In this video, we're going to talk about some just review stuff with vectors, and we're going to talk about unit vectors and parallel vectors. So, first of all, just a review of adding some vectors. Of course, we just add the corresponding components, so it's just 5 and 12. Now, remember, from a graphical standpoint, this means you went over 3 and up 5, and then you get this new endpoint, and from there you go over 2 and up 7, which gives this as your final vector connecting the beginning to the end. Okay. This next piece, -2 minus 3, so -5. 5 minus 4 is 1. And again, you can sometimes think about this if you were actually doing it graphically, like it's adding a negative. So then you do this one vector, and then you do the opposite of the other vector and add that on. This next piece would be 10 and 20, and of course this is just extending this vector out 5 times. The components of the vector that connect 1, 7, and 1, 7, and -4, 5. Well, we've got to figure out what's happening in each piece. So, of course, from 1 to get to -4, we need a -5 component in the x direction, and from 7 to get to 5, we need a -2 in that component. Again, only because this is our starting point and this is our end point. Okay? And finally, what angle does the vector 1, 5 make with the x-axis? Well, if I go over 1 and up 5, like this, that's my vector. The angle I could figure out with tangent, okay, because I know this is 1 and this is 5. So, of course, the tangent of theta is equal to opposite over adjacent. So theta is the inverse tangent of 5. All right, let's look at unit vectors. So a unit vector is simply a vector that has the same direction but a magnitude equal to 1. And that's the term, unit. You've heard of unit circles, dealt with those. So unit vector, same magnitude, but same direction, but a magnitude of 1. So this initial vector, if I could kind of make this just a little bit bigger, over 4 and up 2, so it looks something like this. The initial length of this vector, or the initial magnitude, 4 squared plus 2 squared, is the square root of 20. Now, the way to make our current vector into unit vector is simply to divide the current vector by the square root of 20. Or you could think about like you're scaling it by 1 over the square root of 20. And that's it. Now think about this. If this were squared, if you were going to find the length of this new vector, this first value squared would be 16 over 20. This second value squared would be 4 over 20. Adding the two together gives you 20 over 20, or 1. And of course, square root of 1 is 1. So it now has a length of 1. Okay. This other one, 4i minus 2j. This is the same as the vector 4, -2. Okay. That I and j, that's all that represents. I is an x direction, j is a y direction. So again, this has a length of square root of 20, so you'd have 4 over the square root of 20 and -2 over the square root of 20. And it's -2, like that. Okay? So unit vector, find the length, and then divide each piece by that to figure out the vector that has the same direction but a magnitude of only 1. Parallel vectors have to have the same scalar multiple that can transform them, but they can move in different directions and have different lengths. So actually I put up 3 that are all parallel, but you actually could have had another one if I could draw it, assume that it actually looks parallel. it could actually even be going in the other direction. Okay, there simply needs to be a scalar that you can multiply one vector by to get the other. So in this case, it's, how can we show that 1, 5, and 3, 15 are parallel? Well, it's because if I took this initial vector and multiplied it by 3, I would get this new vector. If there's some scalar that you can multiply by, and that number can be any integer, it does not have to be a positive value, because of course a negative value would move you in the opposite direction.